So when you're ready, then feel free to make a start.
Okay. Hello, everyone. My name is Fangjing from the University of Strathclyde. And my topic is low insulation coil HTS winding technique for electrical aircraft propulsion. My presentation will be included in 4 parts: the introduction and the HTS machine with NI coil design, including NI coil modeling, and my experiment plan and the experiment result. And also I would give some discussion including the eddy current and losses in the NI coil and the influence of the background field and the influence of turn-to-turn resistivity and to use a turn-to-turn resistivity gradient technique to improve the performance of NI coil. The first is introduction. Many institutes have do some research for NI coil used in the HTS machine because the NI coil have many advantages to use in DC to apply when we apply a DC current. So this is very good to use in a magnet or in the machine rotor. So this machine is designed, demonstrated by NASA in 2018, and this is supposed to use NI coil in a superconducting rotor at liquid nitrogen temperature. And the power rate is 1.4 megawatt, and this is designed for electric aircraft. And the challenge for this NI coil is the challenge to use HTS coil in the rotor is there is a mechanical vibration in the machine, and also there is the core. We need to study on the coil quench and protection, and also we need to improve the power density. First, what is the low insulation coil? The left is the insulation coil, and the right is the low insulation coil. And as we know, we have a multi-layer for HTS tape. There is a superconducting layer inside, and there are some metal from other layer. And the key idea of NI coil is to remove the turn-to-turn electrical insulation of traditional insulated coils. And the advantage of the NI coil is that the current in some condition can go any direction. So if there is a hot pot happen, there is a damage or a quench happen here, the current can go a bypass path to avoid this point and to protect this coil. And this is very good to use this in the machine. So it's good advantage. Some advantage for the NI coil is a very good thermal stability. It allowed a fault tolerant, and then it can enhance the current density because the turn-to-turn insulation is removed. And the NI coil has a higher mechanical strength because the turn-to-turn is very firmly and is very tight. The HTS rotor design with NI coil is simply replace the copper windings with HTS winding to replace the rotor winding with NI coil and apply a DC current. And there is a problem when we apply a DC current in the NI coil, all the current will flow in the superconducting layer, and there is zero resistance in a DC condition. But in a machine environment, the AC magnetic field will induce eddy current and extra AC loss, because the absence of turn-to-turn insulation. So this will increase the AC loss in the NI coil, and this is a problem and a big issue to design a cryogenic system. But for a synchronized machine, the magnetic field generated by the stator will be the same rotation speed of the rotor. So in this case, the HTS winding is stationary related to the fundamental field. So there will be no problem for the rotor, but besides the fundamental field, there is a ripon field from the stator. When we do a Fourier calculation, we found there will be higher order frequency in machine environment, and this magnetic field, the rotational speed is not synchronous to the rotor. So the HTS coil will suffer from the AC magnetic field. So our topic is to figure out the performance of NI coil in an AC magnetic field. The proposed methodology is using a circuit network model. And this is the old model developed by MIT in 2010, and they regard this coil and separate the current in two directions, and assume all the rational current is the same. And so this is a basic model to study the NI coil. A new model is to subdivide it into several arc elements and build a circuit network like this. And we have separated the NI coil into some arc element. And for example, here is an arc and another arc. We can use Kirchhoff's law to use a governing equation, and all the sum of the current will be there in this area will be 0, and in this circle, the sum of the voltage will be 0. And I will demonstrate this model in detail, and we have separated the current into two directions, the radial direction and tangential direction. And this is the governing equation. And in order to calculate this voltage, we induce another virtual coil outside in this model. And the voltage can be calculated using this equation. And here is the material inductance between the case arc element and the external equivalent virtual coils. We have added another copper coil in the model in order to generate a background magnetic field. And here is a new material inductance in the model. And how to validate this model in the experiment? We have wound an NISTS coil wound by a Robel tape from Sunan. And the other copper solenoid coil is wound connected with a power amplifier to generate the background magnetic field. And we from another angle to see the HTS coil position in the copper coil during the test. And we use a Hall sensor in the center to measure the magnetic field inside. As we know, it's very difficult to measure the eddy current in the NI coil directly. So we use a Hall sensor to measure the eddy current induced by the background field will produce another magnetic field. So we can use a Hall sensor in the center to measure it and make a comparison between the simulation and the experiment. And the result from simulation and the experiment are compared to validate the model. Here is some parameter of the NI coil and also the copper coil. The tape critical current is 190 amp at 77 Kelvin, and the coil critical current is 130 amp at liquid nitrogen temperature. And first, we need to measure the temperature resistivity by experiment. The temperature resistivity is a very important parameter in NI HTS coil. We use sudden discharge experiment to measure the temperature resistivity. First, connect the NI coil with a DC power source and use the switch and apply a current from 40 amp to 100 amp. That is for different measurement. And suddenly switch it off and measure the coil, the voltage of the coil. And we can use this equation to calculate the equivalent radial resistance for this coil. And also we can use this for equation to calculate the temperature resistivity for this coil. And in our experiment, we have measured the temperature resistivity is 96.7 microohm square centimeter. Here is the result of the model validation. We're comparing the central magnetic field measured from the measurement and simulation. The purple line insulates the background ripple field generated by the copper coil. And the red curve, it demonstrates the central field by model calculation. And the blue curve is measured by experiment. We can find it a very good agreement between the experiment and simulation. And this is applied to 20.66 amp in copper coil, and this is 40 hertz. We have measured different amplitude of background field and do a calculation in the simulation model and make a comparison between a simulation and experiment. We found it also very good agreement. And we have measured 7 background field, and the main possible factor for the error will be that the temperature resistivity is used from a fast discharge test. It may change in the experiment. We put the coil inside the liquid nitrogen gas out, put it again. It may be changed the temperature resistivity, in fact. And also, the temperature resistivity is assumed uniform among the turn in simulation, while in fact, when we want the NI coil, it may change with, and it maybe change in fact. And other unavoidable error in the experiment, for example, unavoidable inductance capacitor from the environment. And from this model is built by a circuit network, and when the operate current below the critical current, the temperature resistivity is a constant value. Also, the inductance value is a constant, and the resistance of HTS layer is almost 0. So we can regard this system as a linear system. So we can, and our model will not influenced by the frequency and the DC component. So in the further study, we will remove the DC component in the coil. In the real-time operate machine, with the DC current is applied in the coil, but in our study we have removed it. And also this model will not influenced by the frequency, so we have validated this model by some experiment from 10 Hz to 100 Hz, and this result demonstrate for the 40 Hz, and we can go higher frequency in the model study. And details of discussion have been published in this paper. If you are interested in this area, you can find this paper, find more details in this paper. And here's the discussion one, and how the coil performance and how the induced eddy current and loss performance from the background field. In this case, we have do a simulation in 5 points in here from P1 to P5, and this is P1 to P5, and there is a skin in effect was observed in the simulation, and this makes sense because the outer layer had a large diameter and will be coupled most magnetic field from the background. And we found that the maximum current is on the outermost turn, and the P1 and P5 moment is at the weakest point in operation. And the figure on the left demonstrates the eddy muscle current, also the transport current flow in the superconducting layer below the critical current. The right hand side is the radial current density flow through the turn-to-turn contact. And we discussion the discussion about the influence of the amplitude of background field. The maximum current will be influenced by the background field. Our tape critical current is 190 amp, and when the we can see from this figure that below the critical current, the transport resistance in the HTS layer is almost zero, and turn-to-turn resistance is a constant. So the induced current is almost proportional to the amplitude of the background field. When the maximum current above the critical current, then there will be use an EZA power law to calculate the power density, and we found the maximum current will increase slowly. And this is the loss part, turn-to-turn loss part generated by the radial current on turn-to-turn contact. We found when the background field increased, the turn-to-turn loss increased in different frequency. And also in this loss part is generated by the transport current. Before the critical current, the resistance of HTS layer is almost zero, so the transport loss is almost zero. And when the current above the critical current, the transport loss, the eddy current will increase significantly. The loss will increase significantly and will be much higher than the turn-to-turn loss. When the coil operates below the critical current, the eddy muscle loss will be significantly lower than turn-to-turn loss. And also, we discussed about the influence of the frequency of the background field. And we can, from this part, when the frequency increase in different, when the frequency increase, and the maximum current will increase. And higher frequency will lead a more significant non-uniform current distribution in the NI-HTS coil. For example, in this point, the background field is 40 Hz and 29 microtesla. And this very small background field will induce a very big current around 150 amp of the NI-HTS coil. As we said before, the critical current of this tape is 190, so this is a not good operate point. And the time-to-time loss calculated by the relationship between time-to-time loss versus frequency. We found the logarithm of time-to-time loss power is almost proportional to the logarithm of field frequency. And we know that in the electric aircraft system, the frequency may be much higher than 100 Hertz, maybe 400 Hertz. So the time-to-time loss must be considered in the rotor style, in the rotor design. And we also discussed the time-to-time resistivity of the NI-HTS coil. Normally, the time-to-time resistivity of the NI-HTS coil will range from 1 microohm square centimeter to 10,000 microohm square centimeter. It depends on the winding tension, the surface condition, and the material of the tape. And we increase the time-to-time resistivity. We found that the maximum current will decrease. And also we calculate the time-to-time loss. We found there is a peak point here at around 10,000 microohm square centimeter. In the rotor design, this part should be avoided. And we discussed from this figure that if the time-to-time resistivity go almost to 0, then the coil will be regarded as a HTS bug. So the time-to-time loss is very small, but then the HTS bug is very hard to charge. And when we go time-to-time resistivity to infinity, in this case, this is an insulation coil. The time-to-time loss is also very small. And between these two cases, there will be a peak point. We need to avoid this area in the rotor design. And we found that the conclusion is the maximum transport current induced can be reduced significantly by increased time-to-time resistivity. And the time-to-time loss will be a peak area when we increase the time-to-time resistivity. So we suppose one possible solution for the NI coil to use in a HTS rotor is that we can gradient time-to-time resistivity technique using this technique. When we want the NI coil, we can use different tension in different turns. In this study, we can find that the key idea is that we use a higher time-to-time resistivity on the outer turn of NI coil to reduce the current accumulation. And we use a lower time-to-time resistivity is applied in the middle turn to keep a good thermal stability of the NI coil. From the left-hand side figure, we can know that we applied different time-to-time resistivity, and we found the maximum current distribution will be improved. And from this figure, we can find that for the different time-to-time resistivity, if we want to reduce the current amplitude, then the time-to-time loss will increase. We can in future study, we can find to optimize solution between the current amplitude and time-to-time loss. If the current amplitude is reasonable and the time-to-time loss is reasonable, then this can be used in a HTS machine. Okay, the conclusion, our model has developed to calculate the current distribution in the NI-HTS coil, and the opposite magnetic field from this model agrees well with that measurement, which validates the model. And the AC loss is generated by the on the turn-to-turn contact by the eddy current. It's very hard to measure the AC loss in the NI coil in the experiment. So so we only validate the current distribution in this coil, and all the AC loss is calculated by simulation. If the eddy current calculate was reliable, and we believe turn-to-turn loss from the simulation should be also reliable. And we developed a numerical model based on the circuit network for the HTS coil in a ripple background field, and this is validated by the experiment. We also studied the distribution of induced eddy current and AC loss by this model, and also we discussed the influence of turn-to-turn resistivity and field frequency and amplitude on the eddy current is discussed. And this study has developed a model for NI coil in a uniform magnetic field. In future HTS machine design, we can use this model for a specific machine design. And this model is very important to provide the data to optimize a machine design to reduce eddy current, also reduce AC losses in the HTS rotor. Okay, thank you.